All right, so magnitude or modulus. So suppose z is equal to x plus yi is a complex number So basically, whenever you see their definition here is saying that some complex number is defined as constant real number plus a real number with a imaginary component. So for example, so we know what we're talking about here, the number 0 is technically a complex number because I could write 0i, right? Or I could say the number 2 plus 1i is also complex. So complex meaning it is a combination of the complex plane, the imaginary numbers with the real numbers. So they combine them together to create the complex plane. That's all that this means. So it's just some complex number, in other words, some imaginary number. But when you hear the word complex, that could be technically just a real number, or it could be a real number with an imaginary piece, etc. The magnitude of z denoted by the absolute value bars is the distance from the origin. To the point x comma. So the magnitude z is equal to the square root of x squared plus y squared. All right. So first thing I want to mention, if you have this complex number, x plus yi, then the z bar is going to be the conjugate, x minus yi. Number 2, z equal to x plus yi can be rewritten as r cosine plus r sine theta times I, or simply as cosine theta plus I sine theta. Number 3, the magnitude of z is also equal to r. E to the I theta is equal to cosine theta plus I sine theta. This is actually Euler's formula. 5. R times cosine theta plus I sine theta is equal to R times E to the I theta. You can rewrite it this way. This is really just an extension of number 4, right? Because the E's inside, so this part. Okay. And the rest are based on the rules of exponents, but I'm going to go ahead and give them to you anyway. suppose that z1, the first complex number, is equal to r1 times e to the I theta 1, and z2 is equal to r2 e to the I theta 2 are two complex numbers. Then the following is true. For 6, you multiply z1 times z2, you would end up with r1 times r2 e to the I times theta 1 plus theta 2. If you doing your algebra, rows of exponents. For 7, if you were to divide them, r1 e to the I theta 1, show the in-between step this time.
Can you move your paper up, please?
Yeah. Would end up with r1 over r2 times e to the I times theta 1 minus theta 2. Number 8. I'm trying to give you all the formulas up front, that way you just find them easy. R times e to the I theta is equal to r times e to the I times theta plus 2k pi, where k no, 1 second. De Moivre's theorem. If z is equal to r times e to the I theta is a complex number, then z to the n is equal to r to the n times e to the I times n theta, where n is greater than 1 and n is an element of I.
What's that little thing next to the z to the n?
Right here?
That's
That's
r and z.
yeah.
R to the n and z to the n.
Yeah, z to the n is equal to r to the n. Yeah, I'll write it better. Or bigger, rather. It's not better.
What's the symbol between the N and I on the end?
N theta?
No, on the to the right of that in the paper.
Oh, I'm sorry. I used this is math notation. N is an element of the integers.
Okay.
Sorry, I don't know if I've mentioned that notation or not. Okay. Plotting a point in the complex plane. Ah, correct. Start the brother's dog. If W is equal to R times E to the I theta is a complex number, and n is greater than or equal to 2, n is an element of I, so n is an integer, n is greater than n is equal to or greater than 2, and W is not equal to 0, then there exists n distinct complex roots of W. Given by the following. So z sub k is equal to the nth root of r times e. Check this formula. Into p or into e to the I times 1 over n times beta plus 2k pi. Where k is equal to 0, 1, 2, all the way to n minus 1. So k will only cycle to 1 below whatever n is. Should be everything we need for this section. First example, plotting a point in the complex plane. Plot z equal to cube root of 3 minus check I wrote this correctly. It is I. Okay. So let me find a nice picture for you. Okay, show you this here real quick. So traditionally we have the x-axis with the real number. So think of your number line, negative and positives, your real numbers, going this way. Combine it with the imaginary axis. So it's kind of like the imaginary is the y stuff. It's just a little bit different, but we're going to treat it that way. Okay. So they combine two sets of numbers together. Because the imaginaries are separate from real numbers, but when you combine them, you create a complex blank. So now everything that was in the real numbers is now in complex blank. That's all I want you to know from this idea. Okay, so when you graph this, right, just like we saw in that picture, this is the real axis, this is the imaginary, so we're just going to figure out what exactly is square root 3. Square root 3 is
1.65.
It's pretty close. I got 1.73. Let's just use that number here. So here's 1, here's 2, here's a negative 1. So treat this as square root 3 comma negative 1. So this is the imaginary component. This is the real part. So you go down negative 1 and out to about 1.7. So it's about here.
Can you adjust that camera a little bit?
So basically you're almost treating it like x and y. So the imaginary piece is going to be on the vertical axis. Okay. So the first couple of questions in your homework will be simply just plotting these numbers. All right, let's go to another type of example. After the first few examples of just plotting points, they'll ask you to write z equal to root 3 minus I in polar form. So they're going to have you convert this to polar. And exponential. So we're going to use those formulas that have the exponents to change it to either one. Okay. So write down everything that we know. Consider the x piece equal to square root 3, the y equal to negative 1. R squared we know is equal to x squared plus y squared, which implies that r is equal to the square root of this. Okay, so r would be equal to square root square root 3 squared plus negative 1 squared, which will be square root of 4, right? So there's r. And last time we talked about how r cosine was equal to x, which means that cosine theta is equal to x over r. So that means sine theta is equal to y over r. So almost have everything we need. We do need the angle. So to find the angle, let's plug in everything we know. This is going to be square root 3 over 2, right, for cosine. And sine would be negative. So what angle would give us this on your unit circle?
I don't have it pulled up. 1 sec.
7 pi over 6.
Yeah, 11 pi over 6, right?
That's what it looks like.
That's right. Okay, so then plug all this into our formulas. Use the z formula. So z is equal to r cosine theta times, or plus I sine theta. R would be 2 times cosine of 11 by 6 plus I sine 11 by 6. So this would be your polar form right here. Space. Okay, so now to get the exponential, use the exponent form. Thank you. All right, let's go ahead. So we have the polar. So now use the exponent. So it's going to be this guy. So z equal to r e to the I theta. So you already know r, so that'd be 2 e to the I 11 pi 6. This would be your exponential. So these are your answers. So really we're just using the formulas and the point they gave us to fill out. So the homework will ask you, giving a complex point, z value, go to polar exponential, and then they'll ask you, give you a polar and ask you to go to complex and exponential. They'll have like backwards and forwards. At 6:45. Let's come back at it's about 7:55, around there somewhere. Okay. So plot the point that corresponds to z equal to 2 times cosine pi over 6 plus I sine pi over 6. In the complex plane. Right, so just find the r and theta, which is pretty easy to do, right? They're right there. So z equal to 2 cosine pi over 6 plus I sine pi over 6 is equal to 2 times e to the I pi 6. So theta's up top, so our point would be, our r theta polar coordinate would be 2 comma pi over 6 r. All right, plugging these values into your unit circle, using the unit circle, give you 2 times square root 3 over 2 plus I times f. Multiply the 2 through, and we'll get square root 3 plus I. So there's your complex number. Now we can use the r theta to plot it using our polar coordinate. Go to I over 6, well, 2. So that'll show you. Okay, so this right here, so here with the instructions. Yeah, I forgot to add something. Just got carried away. So add something. Sorry about this. I'm trying to shorten this up. Plot z equal to 2 cosine pi over 6 I sine pi over 6 in the complex plane. And convert it, that's the part I forgot, to rectangular. So this part right here is what they want. So in your homework, they have part A, B, C, right? So part A will most likely be just plotting this part. And then you'll convert this, which is really just plugging in the angles, and give them the rectangular value. Okay. That'll be a part B or C. Is there any questions on these first two so far?
So square root of 3 plus I is rectangular.
So this is the polar form. Using your Z form that you can end up with rectangular coordinates. You can plot directly right, on here using the angle and radius. In the first half of the homework will be plotting points, either given polar, given the Z number, converting backwards and forwards, and then after that we start finding the products. Find the products and quotients of the complex numbers. So if Z is equal to 3 times cosine of pi over 9 plus I sine pi over 9. And W is equal to 5 cosine of 5 pi over 9. Gosh, what the
Adjust your camera when you get a chance.
Yes, thank you. Okay. Plus I sine 5 pi. All right, so the last question like this. Part A would be something Z times W. There's the product. You can technically FOIL all that out, but it would be easier to use your formula. So write them together, but don't actually. So Z first. Times W. So at this point, you're going to switch to the exponent form. That way you don't have to deal with this. So remember that this formula, you can write your cosine theta and I sine theta as E I theta using Euler's formula. Let's go ahead and do that. This would become 3 times e to the I over exponent big there. 3 times e to the I by 9ths times 5e to the I 5 by 9ths. So I'm converting this inside stuff and leaving 3 and 5. So that will become 15 times e to the I. And the rules of exponents tell us to add this, right? So we're going to have pi ninths plus 5 pi ninths, which will give us 6 pi ninths, which reduces to 2 pi thirds, right? So once you have this, you can then convert back to the original form. Complex number, get away from the exponent, and just say that this product is really just 15 times cosine 2 pi thirds plus I sine 2 pi thirds. So in a way, using Euler's formula, we were able to avoid this messy product and using identities and trying to figure out how the heck do they combine, getting to here. That makes sense. Why it's helpful. So the quotient will be similar. So let's move on to something else. It's just rules of exponents. Express 2 cosine excuse me, pi over 9 plus I sine pi over 9.
Wait, it said find the quotients too, right? On the last example.
Yeah, I'm going to skip the quotient, unless you want to do it. It's not a big deal. You want to do the quotient?
Nah.
Okay. It's very similar. You just divide, and then instead of the plus here, you just show it in case somebody doesn't know. The only difference would be is instead of a product, you'd have a division, but at this point, you would have 3 over 5 and a minus here. That is the only difference. All right, so now let's talk about de Moivre's theorem. So the reason it's useful it's because if you have a high power on a sum of trig functions, you don't want to FOIL this out 3 times, right? Nobody wants to do that. But you can use de Moivre's theorem to help you out. So what you want to do is express it in exponential first. So we're going to end up showing it in exponential and then rectangular. Okay, so I'm gonna go write a note here. Exponential form is r e to the I theta. Rectangular form is x plus yi. So I want to change this guy into both of these forms. Okay, so let's start with that. Let's write it down again. 2 cosine pi over 9 I sine pi over 9 put the changes into exponent first. It'll be easier to deal with this these powers. So that'd be 2 e to the I pi ninths cubed, right? Using our formula. So then rules of exponents say that this is just 2 cubed times e to the I pi ninths cubed, which would be 8 times e to the I, and you're going to multiply this guy here. So 3 times pi ninths would be 3 pi ninths. Okay. In case you forgot, this is the rule that we're using from way back when we did exponents, right? If it already has a power, you multiply them together, right? So this already has a power, so you multiply this guy by 3. That's what we got. That's how you get here. So final answer for the exponential form would be 8 e to the I 5/3. Part A, right? Exponential. But once it's an exponential, it's easy to get to rectangular. So you want to start with this guy first. So now 8 e to the I 5/3 is equal to 8 times cosine 5/3 plus I sine 5/3. Once you're here, just plug in the values and use your unit circle to get to rectangular. So 8 times cosine of 5/3 is going to be
Positive 1/2.
yeah, so half, right?
And then square root 3/2.
Thanks. So at that point, multiplied by 8, pretty much done. So we get 4 plus, oops, 4, 3. So this would be rectangular. Any questions on this problem here? All right. Do a similar one, but this time it's not going to be in the trig form. 1 plus I to the 5th in exponential and rectangular. All right. So when I give it to you in this form, you have to solve for r, you have to solve for here. So currently we have x equal to 1 and y equal to 1, which means that r is equal to square root 1 squared plus 1 squared, root 2, right? We got that. So now we can convert. Try to get it into that form. So I'm gonna do some weird algebra right here. So I want the r to be in front, correct? That way it can help us get to the polar form. So what I'm gonna do is factor a root 2 that doesn't exist, then put it on the bottom to create balance. You see how if I multiply this through, I would end up here? And if I were to rationalize, this would be root 2 over 2, right? And we know the only place we're getting x, where we have a x and y, 2 over 2, that are positive, is going to be cosine of pi over 4. Once I have this, I can get to exponent form, no problem. Okay. So now we know that. Is there questions? Yeah, so this would become 2 e to the I pi over 4. So now we can say that 1 plus I to the 5th is equal to square root 2 e to the I to the pi over 4 to the 5th, which would end up at 2 to the 5th times e to the I pi 4th to the 5th, which will give us 2 root 2 is 2, 4 root 2 times e to the I 5 pi 5th. Doing our algebra there. Then this is the next one. Okay. Now change this back to polar form. That would be 4 root 2 times, because that's my r, cosine of this angle now we can get to rectangular. Well, go ahead and evaluate these values here, these functions. Cosine of pi over 4 is going to be a negative root 2 over 2. Sine at 5 pi over 4 will also be negative. Multiplying this through would give us negative minus 4. This would be rectangle. Do you have any issues with this example? Finding complex roots. Of negative 1 plus square root 3i and express it in exponential negative 1 plus square root 3i so x is the negative 1, y is solve for r. That would be sum of these squares, so that squared squared. Two. So we got r. So try to get into exponential form. So when they ask you to find complex roots, you're going to need it in exponential form. Then you're going to use a specific formula. We use this guy here. Z. So k is equal to the nth root of r times e to the I 1 over n. I wrote this at the beginning, but just writing it here, we have it in front of us. Theta plus 2k pi. And k will range from 0, 1, 2, all the way to the last number before n. Right. Okay. So here we go. Negative 1 plus root 3i is equal to 2 times, if I factor a 2 out, I would get negative half plus root 3 over 2. Now this angle is going to happen at 2 pi thirds. I'm going to change this into cosine 2 pi thirds plus I sine of 2 pi thirds. Then go to exponential so we can start working with it. This would be 2 e to the I 2 pi thirds. So we're going to use this guy up here, help us out. So we need to decide what is our n. So z sub k, you go to n to the nth root of r,
Can you move your paper up? Thank you.
e to the I 1 over n, should I write it one more time? It's 2k. All right. So the n, I'm going to try to rewrite this guy as a third at the bottom. So that means that my k is going to cycle 0, 1, 2. This k has to be all the numbers before n. So z0 would be third root. So okay, n is 3. So in the n of 2 e to the I 1 over 3 times 2 pi 2k plus 0 actually, because k will be 0. First one, z1. We have to plug that in a little bit. Cube root of 2 e to the I 2 pi thirds. Let's go to the next one. Cube root of 2 e to the I third times 2 pi plus 2. Yeah, this k would be 1. So that would give us yes. Sorry. This should be it. Yeah, there. So you got to cycle from 0 to 2. So there's 0, 1. 1 would be, add these fractions, right? So that would be 8 EI 100 times thirds. Let's go EI B. Oops. Short. E to the 8 pi ninths I. The last guy here. Z is, or n is 2, the last in the cycle, the last root. So 3, 2, e to the I 1/3, 2 pi thirds plus 4 pi. It's k is 2. So that would give us cube root of 2 e to the 14 pi ninths. So my answer would be this guy here, this one, and this one. So to make sure you, yes, once you get it into exponential, all you need is n, and you can start using the form. Just remember that you have to go up the k until k stops one integer before n. So 0, 1, 2.
How did you pick n?
N is it's gonna be the value underneath here.
Okay.
Check one thing.